Hi guys, and welcome to the third video. This time we're going to finally get to probability theory and talk about the basics of probability. But first, we need to talk about one last thing from set theory, and that's functions. We're going to use the definition I teach in discrete math for functions. So let A and B be sets. A function from A to B is a subset of their cross product, such that for each element of A, there's exactly one pair in the subset that has that element. But mathematically, we write f goes from A to B, and that's this f colon A arrow B. We call A the domain and B the range of the function, and instead of writing it as sets, as x, y is an element of R, we write f of x equals y, or sometimes we say f maps x to y. So for example, let A be the set 1, 2, 3, and B be the set A, B, C, D, and let R be the subset of their direct product 1b, 2c, 3b. Then R is a subset of A cross B such that each element of A does appear in exactly one pair. Notice that it has to be exactly one. So, for example, 1 appears in one pair, 2 appears in one pair. They don't appear in 0 pairs. There's nothing that doesn't appear, and there's nothing that appears more than once either. Then, we've defined a function, f, which maps from A to B. F maps 1 to B, f of 2 is C, and f of 3 equals B. Also, recall that last time we talked about omega as the symbol we're going to use for the universal set. So if we're rolling a die, omega is the numbers 1, 2, 3 up to 6, and if we're flipping a coin, omega is the set heads and tails. Now we can finally define probability. A probability is a function from the power set of omega to the real interval 0 to 1, with the following two rules. First, the probability of omega equals 1, which just means that omega includes all outcomes. So, for example, in the coin flip, we don't want to make omega the set just heads, because then we might flip an outcome that isn't an omega. Or on the die roll, we don't want to get an outcome that isn't 1 in omega, so we don't want to take omega to be the numbers 2 through 6, for example, because if we roll a 1, we're going to be outside of omega. The second property is a little bit more difficult, but using these two properties, we'll build up all the rules of probability. The second property says that if we have a sequence of events, A1, A2, A3, A4, and so on, that don't overlap at all, so their intersections are always empty. Then, the probability that one of those events occurs is the sum of the probabilities of any one of those events occurring. That is, the probability that something occurs in that list is the probability of A1 plus the probability of A2 plus the probability of A3. We can just add up their probabilities. And since we're doing probability, from now on we're going to call omega the sample space and the power set of omega the event space. And any element of P of omega is called an event. That's a little bit informal, but it's going to be okay for this class. First thing that we want to actually compute using those axioms is the probability of the empty set, the set with no elements. So we're going to use part 2. We're going to let A1 be omega, the universal space, and A2 and A3 and A4 and every other set in the sequence is empty. Well, to apply the second rule of probabilities, we need to make sure that those are disjoint sets. But that's actually an obvious statement in this case, because anything intersected with the empty set is empty. Then we do the computation. Let's see, line 1. So 1 is the probability of omega. That was part of the definition of a probability, that the probability of omega is 1. And that's the probability of the union from 1 to infinity of the AIs, because A1 is omega, and A2 and A3 and so on are all empty. But whenever I union that all together, I'm going to just have omega. So all I'm doing there is substituting the identity that omega is the union from 1 to infinity of the AIs. Now, since those are disjoint, I can apply the second rule and say that that's equal to the sum from 1 to infinity of the probability of the AIs. And to get the very last line, what I'm going to do is I'm going to plug in what the AIs are. So A1 is omega, and then I'm going to add A2, A3, A4, but those are all the empty sets. so it's plus the sum from I equals 2 to infinity of P of the empty set. And finally, I'll do one more substitution. So the probability of omega, as we said at the beginning, is 1. That was the first rule of probabilities, so this equals 1 plus the sum from 2 to infinity of the probability of the empty sets. But the probability of every set is some value between 0 and 1, because the range of P is the positive real interval from 0 to 1. So the only way to add up that same number, actually, over and over again, infinitely many times, get 0, is that number must be exactly 0. So the probability of the empty set is 0. That means something in our sample space always occurs. Now we're going to use this to derive even more rules from probability. So in a lot of cases, like when we're flipping a coin or rolling a die, we don't really want to consider infinite sequences of disjoint sets, because almost all of them are going to have to be empty. That's the only way to have that many sequences of disjoint sets. So the next statement is that the second rule for probability also works for a finite sequence of sets, so if we stop at some place. For example, the collection A1, A2 through AK, and we stop at K, if they're all disjoint, then the probability that one occurs is the sum of the probabilities of each one occurring. To show that, let AK plus 1, AK plus 2, AK plus 3 all be defined as empty sets. So now we've made an infinite sequence out of A1 through AK by just letting K plus 1, K plus 2, and so on all be sets that are empty. Then the probability of the union from 1 to K of AK is the same thing as the probability of the union from 1 to infinity of AK, because all we're doing is throwing in empty sets, so they don't add anything to the actual set. That's just an identity on sets. And then the second rule of probability once again says that that union is a sum, because it's a disjoint union. But the sum from 1 to infinity of the probabilities of the AI is the sum from 1 to K of the probabilities of the AI, because K plus 1, K plus 2, and so on, those are all the empty sets, so the probability of empty set is 0, and you're just adding 0. So therefore the probability of the union from 1 to K of AK is the sum from 1 to K of the probability of the events, AI. Now let A be any set in omega. Then everything is either in A or it's not in A. So A union its complement is the entire sample space omega, and A intersect its complement is empty, because nothing is in both A and not in A. So from the first rule of probability, 1 is the probability of omega, but the identity says that omega is A union A complement, and those are empty. Since that's two disjoint sets that are unioned together, we can change the union to a sum. So that equals the probability of A plus the probability of A complement, which gives us the identity that the probability of A complement is always 1 minus the probability of A. Bigger sets have higher probabilities of happening. What I mean is, let A be a subset of the set B. Then we can write B as A union the elements that are in B but not in A. So A union B intersected with A complement. Notice that A intersect B intersect A complement is empty, because again, nothing can be in A and not in A. Therefore, the probability of B, which is the probability of A union the set B intersect A complement, can be divided into the sum, the probability of A plus the probability of A complement intersects B. But because the range of a probability is the positive interval from 0 to 1, the probability of B intersect A complement is bigger than or equal to 0. So dropping that, we get the inequality that if A is contained in B, then the probability of A is less than or equal to the probability of B. Last, we want to talk about the rule of inclusion-exclusion. Let A and B be any two events in in our space, we can write B as the union of the things in B and A with the things that are in B but not in A. So the probability of B is the probability of A intersect B plus the probability of A complement intersects B. Subtracting over, we get the probability of A complement intersects B equals the probability of B minus the probability of A intersect B. Similarly, A union B can be written as, or it's equal to, the elements of A unioned with the elements that aren't in A, but they are in B. So A union B intersect A complement. Then the probability of A union B is the probability of A plus the probability of A complement intersects B. Now we can substitute for the probability of A complement intersects B, which we just showed was the probability of B minus the probability of A intersects B, and that gets us the inclusion-exclusion rule, that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersects B. The reason this is called inclusion-exclusion is because we want to count the probability of A union B. So what we do is we add in the set A and the set B. That is, they're both included. But whenever we count everything in A and everything in B, we've counted any of their overlap too many times. So then we need to exclude A intersects B one time. And so we subtract the probability of A intersects B. That's all for this lesson. So I'll see you next time. Bye.